This is the brief on the fundamental roles of the Laplace-Beltrami operator. So think of this operator as a kind of universal decoder for geometry. It's absolutely crucial in fields from differential geometry to theoretical physics, because it basically translates really complex spatial ideas into a clear mathematical language we can actually use, no matter what coordinate system you're in. Okay, first up, its main job is geometric interpretation. What it does is it measures the local curvature of a scalar field, and that's just a value, like temperature or pressure, at every single point in space. And here's the key. A negative result from the operator, that signals a peak, where things curve downward, like the top of a hill. A positive result means you're in a valley. And when it's zero, that's right where the curve flattens out for a second. Second, its real power comes from how it's generalized using tensor calculus, which frees it up from any standard coordinate system. Now, this universal form uses something called the inverse metric tensor and Christoffel symbols, but don't worry about the jargon. The metric tensor just describes the basic geometry of the space, and the Christoffel symbols tell the operator exactly how the coordinate lines themselves are curved. It's how the math accounts for the actual shape you're working with. And finally, this generalization means we can get consistent, accurate results literally anywhere. You can feed it the right geometry data for any system, Cartesian, cylindrical, whatever, and the operator just works. It makes sure the math holds true no matter how you look at the world. This operator is the fundamental engine for turning complex geometric shape into predictable calculations universally.